To start off, we're going to start off with the math behind linear regression, and then we're going to code a specific project in Jupyter Notebook for an agricultural dataset. So we're going to start off with the math behind it and then apply that. First off, we need to understand what is linear regression before we even code it up. Linear regression basically means if one value increases, the other is going to change, the word linear. So if you have this specific graph, if the value of x is to increase, the value of y will go up. If the value of x is to increase, the value of y is going to go down on a constant rate. That's what it means. Regression just means you're predicting things that are continuous. So for example, the salary can be 0, 20,000, can be on a scale from negative infinity up into infinity, although salary is from 0 to infinity, but it's like any value that's continuous is basically regression. That's problems that you can apply linear regression on. So for example, you can want to if you want to predict the salary of a person given the years of experience that they have, or the interview mark that they got, the degree level that they have, the certification that they have, you basically call this the output y, and all of these are called x1, x2 at the bottom, x3. All of these are called input features. So that's what all of these are. They are input features, and effectively your goal is to try and find the relationship between y and x, this relationship h that is popularly known as an hypothesis. Okay, it's just a word that we made up. Doesn't really mean much. So x and then y. The goal is to learn this relationship that maps x and y. Because we know that for linear regression, y is directly proportional to x. So y will be equal to mx, some constant x. So if you think about this, if you look at a normal graph like this, what it means is that if this is x and this is y, m can be 2, for example, which means that if x is equal to 2, y will be equal to 4. If x is equals to 4, y will be equal to 8 because m is equals to 2. So m basically dictates how much y will change if x is going to change. Okay, so we can think about this and say the value of y is going to be proportional to x1, x2, x3, x4, x5 up until xn. So we can introduce the same m that we had, but in this case we're going to call it theta 1, and then have theta 2, theta 3 up until theta n xn. So this is what we're going to call a weight. Okay, or sometimes it's called a parameter. But think of it as y is equals to mx1 plus maybe m2 x2. You're just having different gradients for multiple different variations. So you're having different parameters for multiple values of data. Okay, then the last thing that we're going to add to this, so y is going to be the outcome that we can get out. The last thing that we're going to add to this is going to be b. This is effectively what we call the bias, what we get out without any influence of x1, x2, and x3. So for example, without any years of experience, without any interview mark, without all of this, what value of salary do you have? And it's possible to have a salary without any years of experience. So that would be the bias that you have without any influence of any input feature. So it's very possible to condense all of this and just say x. Okay, so let me delete this. So it's very possible to condense all of this and just say theta, which is equal to theta 1, theta 2, theta 3, and x, which is going to be equal to, let me put capital letter X, which is just going to be equal to x1, x2, x3. It's very possible to take the dot product of these two things. So if you were to say this times this dot product, you get this whole expression. So it's very possible to just say our prediction, which is h of theta. This is just a notation, right, to standardize things across research papers. So this is what we call a prediction, is effectively going to be equal to theta x plus b. So what this means is that theta x plus b, which is our bias term, this is going to be the prediction, the value of y that we're going to do. So the whole point of linear regression is to learn this value of theta and to learn this value of b, such that if I were to give you a new value of x, if you plug it in, it can give you a prediction out. That's the whole point of machine learning. And in order to do that, we need to introduce very important things. So the first thing that we're going to introduce is something that we call the mean square error. Okay, what is the mean square error? So if you make a prediction, remember the notation for a prediction is just this, and if you subtract the actual value that you have, so a prediction can be maybe theta is equals to like 20, 10 or something. You do the dot product, you get a certain prediction out. Maybe it's like 10,000. If you look at y1, it's this specific amount. So the error is how off it was from that value. So we do it like this, but you realize that, you know, it can be positive, it can be negative. So in order to punish very big errors, or in order to minimize the effects of negative and positive canceling each other, we can square this up. Okay, so that's what we call the square error. Mean just basically means find the average of all of these errors that you're going to get. So add all these things up. So you can add h theta x1. So this one in the top just means the first example, minus y1. You can also find h theta x2, which is the second example. This is x2. And then you subtract y2, which is the second example. And you can do all of that up until m specific examples. So if you were to sum that up, right, this is this notation. From I is equals to 1, and put an I over here, and put an I over here. What you're effectively getting is the sum of all those errors throughout all these examples up until m. Okay, so this will be I is equals to 1, I is equals to 2, etc. Okay, so you're going to get the sum of all this, and if you divide by how many they are, which is m, you're going to get what we call a mean square error. Turns out in machine learning, we call this J, which is some function that relates theta and beta. So turns out that J is actually called the cost function in machine learning, right? Cost just means, tracks how expensive it is. A very high cost means that it's very bad. It's a very big error in machine learning. So it's the same thing. We take the same concept and we just rewrite that specific thing, but in this case, it's going to be in this specific form. Okay, and then we put this 2 for convenience. Like, I'll explain why this 2 is here. We just put it because it doesn't really change the meaning of the cost function. If the error is very big, putting a 2 here is not going to change anything. So we're going to explain what that is. And the whole point is basically to use gradient descent to find values of theta. So that's how we actually find these values of theta and beta. There are other methods that we are going to use. So in this video, we're only going to use gradient descent in coding up our program. So what is gradient descent? The way I like to understand gradient descent is if I were to give you a function, f of x is equals to x squared. So like this, and this function is effectively something like this. So we're going to put f of x over here, and this is going to be x. This will be fine, right? It doesn't change anything. So I would like to replace this. I would like to change this and say this is j of theta. And I'd like to change this and say this is theta squared. So you can agree with me that this will be j of theta. And you can agree with me that this will be theta, right? We can agree with this notation over here. So this is a function. It's equal to something squared. Okay. So you can plot a graph on this specific thing over here. And these are basically all the errors that you can make, or the costs, the sum of all this. This is basically going to go here with respect to theta, right? We only chose theta, right? You can do the same thing, but for beta, it's just going to be the same logic. You can do the same thing, but for b, it's going to be the same thing. Okay. So gradient descent basically is how can we find this? You can see that if you plot this cost function as a function of theta alone or beta alone, you're going to get a graph. And the whole point of gradient descent, it can be a plane, but the whole point of gradient descent is how can you find this minimum possible error, this minimum possible value that will be over here. That's the whole point of gradient descent. How does it work? Well, you start at some assumption. So you start off at some value, which you're going to call theta initial. Okay, so you're going to start off with some value, which we're going to call theta initial. And gradient descent is basically saying subtract a small step that you can take times the gradient that you have at that point. And I'm going to explain what that is. And this will give you theta final. Okay, in machine learning, we like to say theta is equals to theta minus the small step is basically called the learning rate. The small step that you're going to take is called the learning rate. So we like to call it alpha. The gradient is going to be this gradient with respect to theta. Partial derivative just means find this expression, the derivative, the gradient of this expression with respect to theta, with respect to this theta value, which is over here. Okay, so you start off with some initial value. I'm going to explain gradient descent. You start off with some initial value. You determine the gradient at that specific point. Okay, you determine the gradient at that specific point, and you go here and you look for the gradient at that specific point. Okay, very simple. So we're going to do this. So this is the gradient that you have at this specific point. Now, you can clearly see that if you were to do this, let me make it a little bit brighter. Okay, so you can see that if you follow this gradient, so effectively, what does the gradient tell you? Okay, so in this case, the gradient, if you're doing something like this, and let's say you got a gradient of 10, okay, so let's say this gradient is actually 10, so the change in g will be equal to that times the change in theta. So what would happen if I were to increase theta, right? If I were to increase theta, you can agree with me that this value is going to go up, right? By increasing this change, which is just new minus old, right? By basically increasing this change, or by increasing this new value, you can agree with me that this thing's going to go up. So if you move opposite and make this smaller, this thing is going to go down, right? The cost is going to go down. So that's following the gradient. You find the gradient where you are and you move in the opposite direction to that. So if you're here, if you move and increase the value of theta to go to here, you can see that your cost is going to go up if you follow the gradient and it leads you here. So you follow the gradient in the direction that gives you the smallest possible value of theta. So you go here, you look for this value of theta over here by following your gradient. So the step that you take, you can land anywhere. You can land here, you can land here, you can land here, right? So what you take here is called the small step. And you can see I moved in the opposite direction. My gradient was 10 in this direction, and I moved in the direction of negative 10 in this direction. And I landed up at a new specific value, which was over here. Okay, a new specific value, which was over here. So this will be my new value of theta. I look for the gradient again at that specific point. And if I look for the gradient at that specific point, and I follow it, okay, if I look for the gradient at that specific point and I follow it, again, it's going to lead me somewhere else. Maybe if I follow this gradient, maybe it's now like 5. For example, if I follow it over here, it's going to give me another value. I follow it again until I arrive at this point where the gradient will be 0. So that's gradient descent. Right. The same thing can happen on this side. So for example, if you're on this side, the gradient is negative 10. You just have to increase the value of theta, right? So to increase the value of theta and move in this direction so that it gets bigger and bigger and closer to this, you simply have to have a negative gradient over here. So negative and negative gives you a plus, and your value of theta is going to increase and move towards the minimum possible value. If there is a plus over here, your value and the minus is going to get smaller so that it converges to the value that you need. So this is basically the whole logic behind gradient descent. Okay, so you can agree with me that if you were to change your value of theta by this rule, you get a smaller value of theta. Okay, this rule even applies for beta. So if we were to do this, that same rule is basically going to apply for B as well. So this exact rule that we're using, we can basically apply it for B as well, and this will be with respect to B, because the same thing that applied for theta can also apply for B, because B is also a function of J of theta. We can find some gradient, right? It's obviously going to be more complicated than this, but the same principle is going to apply. Find the gradient where you are, move in the opposite direction until you arrive at the lowest point possible. Okay, so our task is now to find these values, because if we can find the derivative of that function with respect to B, we can update B accordingly, and we can get the final value of theta in B as it's going to converge. Okay, so what can we do in this specific case? In this specific case, well, it's actually quite straightforward, because you can realize that J as a function of theta and beta is actually 1 over 2m. I can drop the summation sign. It doesn't really change much. So it's the error squared. Okay, so it's something like this, the error squared, right? And I know that my error is effectively h theta, which is theta x plus b minus y. So this is basically my error. I know this is true because this is basically h theta of x. Okay, minus y, that's the error. Okay, so it turns out if you want to find the partial derivative with respect to beta, you can apply the chain rule. So it's the same as finding this with respect to your error and finding the error with respect to theta. So in this case, these two can cancel out and you can find the gradient with respect to theta. So it turns out we can do some very, very cool things with this knowledge, because it's very easy to compute the gradient with respect to the error. Why? Simply because J is equal to 1 over 2m, the error squared. Okay, and if you've done integration before, you drop the power, right? So you drop the power, so it becomes 2 times 1/2. You see why there's this 2, right? You see why I said we needed 2 over here. I hope now it makes sense, right? Because it's convenience. They knew that we'd find the gradient, so they have to cancel out. And error, and you subtract 1 from the power. So you do this. So basically 1 over m of your error is going to be the specific value. And if you were to compute the derivative of the error with respect to theta, you can basically realize that the error is actually theta x plus b. So the derivative of the error is just going to be x, right? The coefficient of theta is x, b is a constant, so it goes away. So this is basically what you get. So the partial derivative of j with respect to theta is going to be, in this case, 1 over m, your error, which in this case is h theta of x minus y times the matrix x. Okay, turns out we can do the same thing for b as well. The for b, it's going to be the same thing over your error times your error, okay, with respect to b. And it turns out that the error, again, is going to give you 1 over m of the error. But in this case, if you do this, the derivative of the error with respect to b is just going to be 1, because this is going to be a constant. It doesn't have anything to do with b. So this is going to be times 1. So this is going to be your value of this specific function. So after all is said and done, turns out that you can get any value of b that you want by basically saying the old value that you have minus alpha and the expression of the gradient that you have, 1 over m, and you actually have h theta. So the summation from m I is equals to 1 of h theta of x to the power of I minus y to the power of I. You close that, you can get a new value of b if you just apply this rule. Okay, if you type this in Python, you can get a new value of b, and it converges to a specific value of b. If this is small enough, if you take a very big step, it's a bad move. And it also turns out that theta will basically be the same. Theta minus alpha, the same thing, 1 over m, the summation of our gradient is theta of xi minus y to the power of I multiplied by x in this case, because our gradient has an x over here. So that's the difference between these two things. You code this, you just replace theta with b, and bear in mind that this is a matrix, right? This is going to have a matrix because you have x over here. So theta is going to give you this specific matrix, theta 1, theta 2, theta 3. And x is just this matrix x1, x2, x3, right? This doesn't have its one specific value. Because we don't have a specific value of x, it's just computing the sum of all these errors as a number. Then it subtracts that from of whatever value you have until this converges. So you're going to end up with one value of b. But because of here, we have a specific value of x, which is a vector. So whenever we update theta, we're going to have all of this error multiplied by this value of x1, x2, x3 until it arrives to a new vector. So we're going to talk about now how to code this up in actual Python. So that we can get going in Jupyter Notebook. Okay, in order to start any machine learning project, you're going to need to open Jupyter Notebook. So you just go to your computer and you type Anaconda. If you haven't installed Anaconda, check out a video that I made on how to install Anaconda. So if you do this, this basically opens up this Anaconda terminal, and you can just type Jupyter Notebook, right? This is just to open up your Jupyter Notebook. If you don't know what I'm doing here, please go and look at the video of how I install Jupyter Notebook. Okay, so if you wait for this, this is going to run your code, and it's going to redirect you to a whole entire page. It's going to lead you to this specific thing. So it knows your whole folder, and it shows you everything that you need. So typically I like going to documents, or you can go to your desktop. It doesn't really matter. It's up to you. I can create a new folder that I'm going to call machine learning. Okay, so this new folder I'm going to call machine learning. Okay, so in this folder, we are going to start creating our projects. So we're going to create a lot of projects together. So the first project that we're going to create is a project for linear regression, right? That's the first. We're going to have another project for logistic regression, and so on and so on. So if we go here, we can create another folder, and this folder is going to be for crop yield prediction. Is the first simple model that we're going to make. Okay, and then if you open this folder, you're going to click on new, and you're going to create basically a new Python file that will over here. And if you click here, we can save its name and say crop yield prediction. Okay, so it's now saved. So in order to start off every machine learning project, we're going to start off by importing the most important libraries that we're going to have. So we're going to import pandas as PD, import pandas. So think of pandas as a workshop. So in pandas, it's a big workshop where you can get all the tools that you want to manipulate data. So pandas is basically where you can create tables. You can use pandas to create a lot of different things. It's very, very cool. And PD, think of it as like a toolbox, right? You go to a workshop called pandas. It's a library, a big workshop, and you can grab any toolbox that you want, right? So within this toolbox, you can open it up, and as you open it up, you're going to pick up any tool that you want, and those tools are called functions, right? So pandas is the workshop as a whole. PD is basically the toolbox, and any function that you call is basically going to be a tool that you're going to pick from that toolbox. So that's how this works. And we're also going to import something called NumPy. Okay, so think of NumPy as another library, another workshop that's used for everything to do with data, right? If you want to do math, you basically use NumPy, and we import it as NP. NP just means the toolbox that we're going to take from that workshop is going to be NP. So NP is a toolbox. You open up NP, you basically pick out any tool that you want to utilize from this specific toolbox inside of this specific library. Okay, import matplotlib is another library, another workshop that's basically used to create specific graphs that you might be interested in, and it's imported as POT. This is basically the same. What toolbox do you want? And in POT, you can get any function that you want, any tool that you want, a hammer, whatever it is. That's the toolbox that we're going to take. So Panda Seaborn is going to be very useful in that regard. Okay, so for now, this is all that we're going to import. And to run a cell, you just click here where it says run this cell and shift enter. So if you are doing this for the first time, I don't recommend that you do this and you put this symbol, the hashtag, and you actually write what it does. So you say it does data manipulation. I'll not be commenting, I'll be talking, but as I'm talking, you can write what it does for yourself after here. So you can have these as your notes so that you can read every single time as you'll be doing these multiple projects. Okay, as with every machine learning project, you need a data set, right? Machine learning is powered by data. In order to do that, you go off to Google and you basically search Kaggle. Okay, if you search of Kaggle, this is what's going to pop up. This is actually called the world's AI proving ground. So a lot of data sets are going to be here. If you click on Kaggle, think of Kaggle as the Walmart of data sets. You go to Kaggle and you get a lot of data sets for free. So if we click on data sets, so there are a lot of different things you can do on Kaggle. You can even participate in competitions. That's pretty cool. If you go here, you're going to search for any data set that you want, for any topic that you want. The one that we're going to use is this agricultural crop yield in India data set. If you can't see it, I've put the link in the comment section below. And if you go here, go on compact, you can basically see everything that you want. You can compare the quantities that you have with pesticide, fertilizer, and your rainfall area. So that's pretty good. You click on download. So this is going to save and download this file as a zipped file to your device. You wait for a couple of seconds. Typically my computer requires me to download again. No thanks. Okay. So we've downloaded this file. It's archive. It's going to save this archive. And if you click on it, it's going to be in downloads. You can basically have this data set over here. So if you click there, we know that if I go to my documents and if I go to this folder called machine learning in linear regression, so Python just basically saves its checkpoints like using this. If I go to crop use, and if I paste here, now this is my data set. Okay. This is what we call, so if you do this, this is comma separated values. It's called CSV. Okay, so this is what CSV means. If you're opening a messed up file, it will look something like this. So this is what we call a CSV. So it's like it takes the first input that you put, the second input that you put, and it just separates them by a comma. So it's comma separated values. So this can be one row in a table, another row in a table. So it's called a CSV, a comma separated values. Okay, so that's basically what it is. So we go back to our Jupyter notebook. So if you're in Google, Sorry, I have a lot of tabs open, but if you go to Google, you're going to have that specific crop yield prediction tab open. Okay, so if we're here, to run a cell, we basically click here. Sometimes I do shortcuts, so it says Shift Enter. So if you press Shift on your laptop and Enter, you basically run by default, right? Okay, so to start off every project, you need to see the data that you have. So the first thing that we're going to do is called exploratory data analysis. So what we're doing is just exploring this data, playing around with it, and having fun. The first thing that we're going to create is what's known as a variable. So think of it as a pot that's going to store the dataset that you have, the ingredients that you're cooking or something like that. So we typically can call it data is equal to. So this is what's going to store everything that you need. So you can call it anything you want. So I'm going to call it Alice, for example, so that you can get the point of this. So PD dot, so PD, think of it as a toolbox that we got from the Pandas workshop. So this toolbox dot, so whenever you see the word dot, it means do something. So dot means open up this toolbox. Open up this toolbox and get what? Get this function that's called read CSV. Then you put brackets over here. So this brackets is basically a way in which we can pass through the file that we want. Okay, so you have two methods. You can either go back to your file, which will be over here. You go back to your file, then you copy this path. So if you click here, you can copy this entire path. It shows you where it is. That's if it's not saved in the same folder. But luckily, I always save my projects in the same folder as my Python file. So it already knows that crop yield, if I rename this, and if I copy this, it already knows that crop yield is the name of my variable. So I put these marks to show that this is my CSV. So you have to put the data type, comma separated variables over here. So what this does is that it reads your CSV file and creates what's known as a data frame. And then after creating what's known as a data frame, it passes it on to Alice, which stores our data frame, right? So I can run this and basically call Alice. And if I call Alice, Alice is going to be this nice and beautiful thing that's called a data frame. Very beautiful. So typically in machine learning, we call this DF. It can be Alice, it can be Peter, Andrew, whatever you want, but we typically call it DF. It's a universal thing when you start a machine learning project. DF just stands for data frame. So initially, the backend is called data frame in most of machine learning, just by default. Okay. Then we run this. Okay, so DF is not defined. Oh, so it's not defined because I didn't run this cell. So if you don't run this cell, it's not going to define your data. Okay, so this is what you get. So you can see that it's showing everything from 0 all the way up until like 19,688, all these different things over here. So what you can do is do a lot of different things. The first thing that we can do is df.head. So it can also be df.tail to get the last values. So if you do this by default, it gets the first 5 values at the top. So 0 up until 4. Okay. So I hope that if you're following these guys, comment, like at the end of everything, comment what I'm saying, and you can create notes, right? If you comment this and you say df is a data frame, right? And you type whatever you want. csv.pd, think of it as a toolbox. Dot means take something from the toolbox. Take what? Take this tool called read CSV, which reads any CSV file. Like type that here. That's how you write notes and you understand machine learning. You don't have to memorize code. Like you can refer to this, but if you write notes, it's easy for you to read. So df.head, what it does, you can also write this, put a comment. df.head, it does this. Okay. So df.head, what it does, it takes the first 5 rows by default, right? They had to pick something. So they chose the first 5 rows to appear, but you can basically feed in anything that you want. You can say 10. It basically shows the first 10 rows by default. df.info is something that's quite interesting. So we typically do this so that we can see the types of data that we have. So for example, integers for crop years, and typically we say that linear regression only happens for continuous values, right? So I can't use linear regression on crop because it's just an object. It's just like a crop. I can't do anything. So this df.info, you can comment again, guys. So df.info basically helps you, and then you go and comment, basically helps you identify the data types that you have. Okay. Then the next thing that we have is df.describe. So df.describe, you can also comment again. So what this means is from df, right? Go to the df guy it goes here. Okay, it goes here, goes to df. Then it's like, do this. So go to df, open up df, and describe df. As simple as that. So what this does is that object does not contain, look at me making spelling errors. Okay, so describe. Okay, if we do that, so now it gives you multiple values that you can use. Count, again, if you go here, you can click this specific thing over here where it says run, and it says cells type. You can change to markdown cell. This is where you can write extensive notes. So it ceases making it a code block. So it's a code block because it's like line 12. It makes it just a text box where you can now write count. Count means, so you're writing notes with me. So as I'm saying count means this, you're typing that out. So that you pause and you type that out so that you create notes for yourself. Okay, I'm going to delete this. Create a new thing. Okay, so count basically counts how many things that you have in total. How many years do you have in total? 19,698. So this is basically how many of these do you have? And you can see that it's the same thing that we had over here, 9,689. Okay, mean is basically the mean value of the area. Standard deviation is how do you deviate from the mean. So if you deviate from the mean by this amount, it is known as standard deviation. Mean is basically the minimum value that you have in your data set. 25% basically refers to how 25% of all the data is below this value. So 25% of all the years are below 2004. 25% of all the area values are below this number. 25% of the rainfall is below 940. So it means that 700, 800, all of those values under 940 corresponds to 25% of the data. 50% is the same thing. 50% of all the years are below or before 2010. 75% of all the data is below 2015, and max basically refers to the maximum value that you have. So this is df.describe. It's used to describe all the data frames that you essentially have. Okay, very nice. The first thing that we're going to do is plot graphs. Now this is nice because this is where Seaborn comes into the picture. So the first thing that we're going to utilize for Seaborn is something that we call joint plot. Okay, so I'm going to put this over here, put a little comment. You can do this with me as well. So it's called joint plot. Okay, what does joint plot do for Seaborn? So joint plot basically gives you the overall relationship between any two variables that you want. This is quite straightforward. So what this means is that, remember, I had a workshop which was Seaborn, and the toolbox that I'm getting is CNS, and the toolbox that I'm getting is CNS. And from CNS, I want to extract a specific tool which joins plots together. That's as simple as it is. Okay, so it joins plots. So joint plot. Now, how does joint plot work? Okay, with code, you're not memorizing this. You're just writing this down, writing some comments so that you can memorize this. Not necessarily memorize, but know what's happening. Or what's important is knowing that joint plot gives you the overall relationship, and you can always look up the code if you want. Okay, so joint plot accepts any value of x that you put. So x is equal to, this is the x value that's going to go on your plot. If you do this and you pass in area, it means that on the x-axis, put in area. Okay, so if you put in y like this and you put this brackets, it means in this case, put in the yield, right? So I want to see how the yield relates to the area. So that's basically how Seaborn works. And then you need to tell it what kind of data should it expect. So it's going to expect data from df. It can also expect data from Alice if Alice was a specific data frame that we created. But in this case, it's going to expect data from df. Okay, and after that, it's going to have alpha. So alpha is essentially a variable that we use. We have to call it alpha specifically. That's what Python or Jupyter Notebook understands. So we're going to call it alpha 0.5. Think of alpha as a number that controls the transparency. Okay, so the higher the value of alpha, effectively, the more visible the data is, or something like that. Okay, so if it's like 0.2, it means the plots are very faint. Right, so we're going to run without alpha, then you can see why alpha is important. One of the things you can learn coding is you can just eliminate certain things and see what the effect might be. So if you run this, if you wait, it does this, Seaborn this, and then it plots this specific graph over here. Okay, so yield, again, it's area. So you can see that most of these points are overlapping. So if I put alpha, okay, so what this does is it runs and then they make it more transparent and they're much easier to see. But we have a problem if you look at this, if you look at your values over here. So if you look at the yield is effectively very enormous, right? You have a yield of 5,000, yield of 1,000. But look at your area. Most of your area is concentrated between 0 and 1. This is 0 and 1 times 10 to the power of 7. That's a very big area in hectares. So you're looking at the area of like maybe all of like India or something like that. I don't know. So the area is all concentrated here. So we want to expand this data so that we can see all of this area. Luckily, so let me make this a run cell. Luckily, we can exploit logarithms. Okay, so log 10, right? Log base 10. So you can put log base 10 on your calculator. Log base 10 of 1 million. What is it? Okay, so log base 10 of 1 million. What is it? Go on your calculator right now, and you're gonna get 6. Okay, and if you punch in log of 10,000, okay, you're gonna get if you punch in log of 10,000, you're gonna get 4. So you can see 10,000 and 1 million are very big, are very different numbers. Sorry, this is not okay. But log of 10,000 is actually 4. These numbers are not that big or that different if you use the log plot. Okay, so this is a very important concept that we're gonna come back to when we're using Python or when we have these issues, or you see it appear and you basically apply these concepts on your own. Okay, so in this specific example, what we're going to do is effectively realize that this specific thing can happen. So if you were to say log 10, right? Remember, we installed NumPy as a library, as a workshop that had this toolbox called NP, where we can pick up any tool that we want. Turns out, if you open up this toolbox, NP, and you extract this tool that can do something very special, log 10. And if you open up this tool, log 10, and if you pass in any column that you want, so you can pass in the whole area, right? It can convert every value into a log 10 value. Okay, so we're going to do that. So if you go here, we can basically say x is equals to np dot open up our chest box, open up our toolbox, get extract log 10. And then we need to tell it. So np doesn't really know what we're getting. So we do this typically. So we say df, tell it that from df, the square bracket means refer to the area inside df. Okay. So simply what this means is that log 10 refer to the area inside df and pass that into the log 10, find log 10 for the whole column. Okay. We can do this so that you can understand it separately. So what we can do is effectively, if you go here, press B to write a new cell. If you do this and if you run this and if you call X, you can see that the area now is like 4.8, 4.86, stuff like that. But before, so if you were to get this, before we passed our area into this, our area was like this. Okay, our area was like this, right? Now it's just been converted to this. It's now on a logarithmic scale. This is quite good. Okay, so we can delete this. I don't need this. I don't need this. Okay. If you're here, this is what it's going to do. So you can do the same thing for yield. Remember, NP, open up your toolbox, extract log 10 from that specific toolbox. After that, those specific brackets, and from your data frame, I want you to pick out the yield and then close that specific, return that specific tool. Okay. Turns out if you do this, if you run, it's going to run, but it's going to give you an error. Okay. But look at that. It's so beautiful. So beautiful. Okay. We're going to explain this in a little bit. If you come up here, something fun is going to happen. They're going to say runtime warning. Part of coding is debugging as well. Divide by 0. What are we doing? We're dividing by 0. That's illegal, guys. You can't divide by 0. Why? Go in your calculator right now. Say log base 10 of 0. Tell me what you see. Okay, a little assignment. You're gonna see something very special, which is math error. You can't divide, or you can't find the logarithm of 0. right? I don't know. I didn't create math. So something smart that we can do is basically find the log of 1 plus x, okay? Find the log of 1 plus x. I don't know how like this guy's thought of this, right? So for example, if you have x is equals to 0, so if x is equals to 0, log of 1, so the log of 1, if you to go here, the logarithmic log base 10 of 1, punch it on your calculator, it's going to give you 0, okay? So the log of 1 is going to be 0. So if you pass in 1 over here, if you pass in like 0 over here, it's going to give you log of 1, which is 0, which is good because it's not log of 0. So it turns out we can actually do NP, like this specific task over here. They saw that it was happening to a lot of people. They were getting this error and they wanted to make our life easier. So they created this specific tool that's called log1p. Okay, log1p. You don't need to memorize this. You can always look it up. Your whole goal as a coder is not to memorize code. Syntax we can always look up. We're lazy. We're lazy with our mind space. So we can remove that 1 and put a p. Remove that 1 and put a p. And you see that miraculously, this error is going to disappear. Press Shift, Enter. Voila. Beautiful. The error is gone. Wonderful. Okay, so now you can see that this is what we call a scatter plot. It's a way in which we can create data points to compare the yield and the area. See that the area is now from 0 up until 17.5. And see that the yield is now from 0 up until 10. So we can easily compare these two. We can see that there's no visible correlation between the two, right? Like we can't really see the visible correlation, but we can also see that the area has this histogram on the top. The yield has this histogram on the top. It's skewed towards these values over here, right? The yield, and you can also find out that the area is like normally distributed, or almost. Most of the area is in the middle. Very few areas are on the outlier. So it turns out that if you to study something, for example, such as area, and let's look at something else very fun, area, and I want to figure out how much fertilizer you apply, right? Based off of the area that you have. I'm thinking that the more area that you have, the more fertilizer that you would like to apply. So I can compare area on the side against fertilizer. If I run this, wow, okay. The bigger the area that you have, the bigger the fertilizer that you're gonna apply. Okay, so these two are directly related. Beautiful. That's usually quite nice. So you can play around with this, have fun, play around with this, and you can basically plot two things, compare if they're very nicely joined together, do whatever you want. But it's tricky because bear in mind, you have area, you have production, you have annual rainfall, you have fertilizer. And our goal is to figure out, well, is there a simpler way we can do this? Is there a way in which we can condense all of our knowledge that we have and write one specific line of code that can effectively just give us what we want, that can effectively give us all of these plots together so that we can easily analyze these relationships together all at once? Turns out we can do that. We can do that quite easily. So I'm going to delete all of this, and we're going to introduce something very nice that we call pair plot. Okay, so it's another important tool that we can extract from the Seaborn workshop and this SNS tool. So it's going to be called pair plot. Okay, what does pair plot do? Well, pair plot, again, you can comment this out. I'm not going to type it. A pair plot basically shows the relationship between every pair of variables, okay? All in one figure. Relationship between every pair of variables, all in one figure. Does that make sense? Okay, so that's basically what a pair plot actually does. So the same thing, SNS. What this means, SNS is a tool that we're going to get from the Seaborn workshop, and we're going to open up that tool. As you open it up, we're going to get this tool called pair plot, or this function called pair plot. What it does is that it plots all of the values all together. Okay, what does this accept as arguments? Well, turns out if you select df, okay, if you select df, df just means pass in the data frame that you want, comma. So this can be Alice, for example. So you first start off with the data frame that you have, so df, you pass in as an argument. That's what pair plot wants. You can see that joint plot wanted you to say data is equals to df. I don't know why they would differentiate that, no, but we do whatever they want. So df is going to be that, and turns out that pepplot expects you to say kind, which is equal to, in this case, it's going to be equal to scalar. Oh, what happened? Okay, in this case, your kind is going to be equal to scalar. So this kind can be reg. So we're going to look at reg next. This reg automatically plots the regression line and everything for you, which is quite nice. Okay. And if we do this, this is going to do the pepplot for all of our data. And turns out we can create what is known as, so you saw that in this case, we just typed in alpha, right? But because pepplot can, accept and draw scatter plots, can draw regression lines, it needs to keep track of what it is that is changing. Okay, so any changes that you make to all of the variables is stored in what we call plot KWS. Okay, so think of plot KWS as a container that basically holds all the options that we're going to do to all of the plots all at once. Okay, so KWS means keyword argument. So with KWS, what it does is it requires curly brackets. Again, this is just syntax. Okay, what it requires are curly brackets, and in those curly brackets, you can basically put squiggly lines. These are the squiggly lines. Okay, and for those squiggly lines, you can basically put in alpha. Okay, so alpha is basically the same thing for transparency, but in this case, it goes inside the square brackets. Okay, then you do this, and then you set that alpha to be equal to 0.4 for transparency. The next thing that you do, shift and enter. You wait. Now, it turns out that Seaborn takes some time. I mean, be patient with it, right? It's trying to understand millions of rows all at once, so it takes sometimes a minute, sometimes 2 minutes. I've had times where it takes like 5 minutes or something like that, where it's like really computing. So give it some time, be a little bit patient, go and grab a drink. You've worked really hard to get to this point thus far. You deserve it. Okay, we're back. So it turns out it plots this nice visualization, but you can see that we have a problem, right? So I'm first gonna explain what this is, then we're gonna go together. So this explores all the relationship in our data. These are histograms that shows how the data is distributed. These are those histograms like across the diagonal. So from here across the diagonal, all of these are histograms showing how the data is distributed. But every other cross diagonal, every other off diagonal shows the relationship between multiple things. So if you want to compare yield and crop year, this is how they're related. Yield and area, how they're related. Yield and production, how they're related. Annual rainfall, this is how they're related. Pesticide and crop year, this is how it's related. Area and pesticide, this is how it's related. Production and pesticide, everything is related and shown on this data frame. The problem is still here because you can see that most values are clustered here. So we can use the same logic and we can basically utilize a whole log 10 thing. Okay. How I like to do this, like there are a lot of methods. The thing is, machine learning is like cooking a cake, right? You can go online and you're going to get 1 million recipes on how to cook a cake. So every quarter that you're going to see is going to have a different way of doing things, but it's up to you to figure out what you want. Some of them are more efficient than others. With practice, you basically learn more efficient methods. But since we're starting, I'm going to start off with a very simple way. Okay, the simple way that I'm going to do this is I'm going to import the file again so that I can change it, right? Because I don't want to change my data that I'm going to use for training my model. So if I do this, I can do whatever I want to my data without having the fear of basically changing my model entirely. Okay, so I copy this, which I think is quite good and quite smart. Okay, so we can do whatever we want to data, play around with it, and we don't have any worry about it changing df, which is our data frame that we're interested in. What's happening here? Okay, good. Cool. What's happening? Okay. So turns out that you can select what you want. So we want to adjust specific columns, right? So we can say columns, cos, and we can basically put in the columns that we want to change. Okay. So we want to change area. Okay. So this is a way in which we can create a list of everything that we want. So area, and then this is annual rainfall. So we do this, annual rainfall, And then, okay, we go here, we do that. Fertilizer, we want to change the fertilizer. We care about that. What else do we care about? We care about the pesticide. We want to scale down the pesticide so we can see that relationship. So effectively, what you can do is you can take data and basically say all the columns in data. So data, take all the columns. This is like indexing. This is called indexing. Putting these two things over here. And it says in data, take all the columns. And if you do that, if you take all the columns and you basically do np dot, okay, log, open the toolbox, get this function, and then start doing things to data, and to data, what we're going to do is effectively apply that to all of those columns on data, which were defined over here. Turns out we do something very cool. And if we were to call data, okay, turns out that area is now 11, 8, annual rainfall is now 7 or something like that. So now we can go here and just call data. Okay, so we've done whatever we want. You can, do whatever you want to this. For example, we just want to visualize this, and what you get we have to wait for a couple of seconds. Okay, this is something that you look at and you can basically see all of these plots that we have, this relationship explored. Okay, turns out you can shortcut this and plot lines on this so that you can see this regression over here quite simply. So you want to see, does this actually form a regression line? And you can do that very simply. So you can go here, copy that same code, go here, and basically change this kind to be reg. So it means plots, scatter plots, as well as lines throughout every single point. Turns out on plot WKS, you can want to change, you might want to change this point separately. You might want to change maybe the color of the line, do very fancy things. You can do that basically because plot as a whole, like remember that plot as a whole accepts, can accept scatter. So plot can accept something called scatter, and it's basically scatter k ws keyword argument for scatter, and that's gonna be so if you do this and you open this bracket, you can put in alpha that you want, any alpha that you want. Okay, so something like that. And then if you do that, you can put maybe 0.4. So now you can separately edit the scatter, and you can put multiple variables inside to just show that you are editing the scatter, right? You can also do line kws. So line kws is something that we do so that we can edit the line separately from the points. Scatter is for these specific dots that you'll be seeing over here, right? Those is nodes, guys, come on. Okay, if we do that, we can basically set this color to be equal to red. Okay, this is quite fun, quite simple. Color, don't get the spelling wrong, and don't use like color with the U. You won't get it right. I don't know why it does that though. I would think that like color is just color for some reason. It doesn't allow that to happen. What's happening here? So color. Okay, so I need nice. Okay, so I need this, and I need this. Nice. Okay. So what this means is that for plot KWS, change the scatter independently, change it to this, change the line independently, and change it to that. So what this is supposed to do is going to give us back all of this, but now it's going to put like regression lines throughout. Okay, we can run that. It takes like a couple minutes sometimes if your data is a lot. So don't worry, don't think it's not running. It does. It just takes time. Turns out if you're very, very patient, this is what you get. Effectively, you have lines that are plotted. So after it's done running, you're going to get these lines pop up. Trust me, it takes a lot of time. Sometimes it can take, 5 minutes, sometimes 10 minutes. So you can just let it run, and then you just go and grab a cup of coffee or something, and you come back and it'll be done. So what you're seeing here is basically all the relationship between these variables. So it's telling you as the years are progressing, the yield is not changing that much. And as the area is getting bigger, the yield was not really changing that much, which is kind of suspicious. I would expect that, which is kind of suspicious because like I would expect that with a higher area, you'd have more yield. So probably this data is a bit off. I don't know, but we're gonna still create a linear model to analyze area, annual rainfall, fertilizer. But you can see that they're almost flat, right? These relationships are not linear with the yield, so this is going to be a very bad model. I can tell already. But we just see whether or not it's good or bad. But it would be a better idea to use linear regression on this specific data. And at this point of exploratory data analysis, that's where you're making decisions as a data analyst to figure out what methods you're going to use to analyze this data. You can now see that linear regression is not the best particular way to do this. So we can now move on to actually building our linear regression model. And we're going to talk about how to build it from scratch using Python.